Hello, today we will talk about the process of building a high-performing regression model for Kaggle computation. So first, we worked with a structured database download from Google Drive, which contain various features about properties, including price, location, and availabilities. And the key objective was to predict the price of properties based on these features while keeping the model accurate, efficient, and generatable. We explored multiple regression models, including random forest, light GBM, XGBoost, CatBoost, neural networks, stacking, actual tree, and TabNet. And our goal for this assignment is to minimize the root mean squared error, or also called as RMSE. As you can see here, this is the part we did. And before a training model, it was crucial to clean and prepare the data. The first thing we did is the data cleaning. We removed all necessary columns and then handling missing values. And for numerical features, missing values are replaced with the main. For category features, missing values were replaced with the most frequent category. Then is the feature encoding and scaling and category covariables or one hot encoded to convert them into numerical form and a numerical feature or scale and using standard scalar, ensuring all variables were on the similar scale. And the last step is to data processing is the splitting the data into training data and which is what we did is to split the data set into 80% of training and 20% validation. This is to ensure that all the model was evaluated on the unseen data. So now is for model selection and training. The first model is the random forest regressor. We start with the simple random forest regressor with 100 trees as a baseline. This model proceed an RMSE of 172.5, giving us a benchmark for improvement. To reduce the complexity, we applied RFE to select the 5 most important features. After selecting the top 5 features, an optimized random forest model was trained with adjust hyper parameters. And then here you can see this is the learning curve we have. A learning curve helps analyze how the model improves with more training data. The blue line is the training error, shows how error changes as the training set grows. And the red line validation is the validation error, shows how well the model generalized. The red validation error line is higher than the blue error line, training error line, which means that the model has overfitting issues. And learning curves analyze shows a gap between training and validation error, indicate a need for regularization or more data. And then is the XG boost. We tune the max depths and then the learning rate, and we added early stopping. Therefore, the RMSE result is 168. And for cat boost, we use the depth equals to 6 and learning rate is 0.05. And then we also use the early stopping. We got a 156.4 for MSE, which is lower than the random forest. This indicates that the better generalization. And the learning curve here shows that as the training set size increase, the training error rise, while the validation error remain relatively stable, indicate that the model generalized well and is not overfitting. So here is the Model 5. This is the fine-tuned cat boost. We used the grade of search CF to test different learning rates and the depths. And the result is 157.92.
We also used a neural network model to process the missing values in the data, normalize the features, subsequently define the neural network and train a model to produce result. But neural networks are highly prone to overfitting problems, and the RMSU result is not very satisfying. And then we have a stacking regressor. In this model, we use three gradient boosted decision trees models, CatBoost, LetGBM, and XGBoost, and fuses their predictions through simple averaging in improve the performance of the regression task. But however, it didn't perform like we thought that the model we have, the better RMSE we have. Then we use the actual tree regressor. Using the actual tree regressor is trying to see how completely randomized model would perform, but in the end, it didn't perform as so well. Then we try a very latest regressor called TabNet regressor. It's a deep learning based tabular data model proposed by a Google research team. Its core advantages over the traditional XGBoost and GBMs because it can automatic selection the importance features, unlike the XGBoost, which requires manual features engineering, and it's more easier to train than traditional neural networks. But if the amount of data is smaller than 100,000 rows, maybe the LGPM is more recommended because they are faster and more stable. In that case, we use the LGPM as our final model. So let's see how we fit the LGBM better. We have established three LGBM model. In the first LGBM, we directly train a regressor with LGBM, no hyperparameter optimization, only use early stopping to control the number of training rounds. It is very suitable to quickly constructing a baseline model, but it's not suitable here because it's maybe not able to find the optimal parameters. So in the second LGBM model, uh, hyperparameter optimizations was performed using Optuner like this one. However, no feature fitting is performed, and the training is still based on the entire set of the features. We can tell it is ideal for the situation in which we want to optimize the model and keeping all the features. But absolutely, in this case, we don't need the entire data set. There are so many features that are not relevant with our questions. So in the LabGBM3, uh, the future fitting is performed first, keeping the most important 50 features to improve the training efficiency and reduce the risk of overfitting. We used Optimal for hyperparameter optimization and adjust the learning rate during final training. This ideal for situation where we want to strike a balance between performance and the efficiency, especially for the problems with large data dimensions, which is very suitable for this case. And we can have some detail looking for this. We use X train and Y train to propose the model and calculate the features importance. Not and then the importance score for each features in the model are extracted. We converted these scores to a panda series, keeping the original feature names and select the top 50 most important features, get the list of them, and use them to train the data. This can help us to reduce the noise because some features of low importance can be very noisy. Eliminating them can help us to improve the generalization, and it also reduce the risk of overfitting because it can absolutely remove some unnecessary tests, can help us to improve the performance. But however, the disadvantages is very obvious. It can only measure the importance of unvariated features and cannot capture the interaction between features. And secondly, because we manually set 50 features, so the top 50 is artificial and cannot be, maybe it's not be optimal. So in the conclusion, to have a better regressor, we changed it out like 8 to 10 regressor models, and finally we decided to use the GBM. And actually, we did have a very good result. And how to fit the GBM to our data set? Like we said, we use feature filtering and hyperparameter to fit our models. And after that, it will help us to with the top 50 features. and give us a very good RMSE.